Okay, let's start. Here we go. So as far as the exam, ready to start? Here we go. So as far as the exam, I have the results from the multiple choice, and I'll post those hopefully tonight, the raw scores from the multiple choice. And I'll make a separate heading in Blackboard so you can just see that. And then I'll try to work on your grading of your free response over the next 3 or 4 days, and definitely have that. Hopefully results will be all compiled over the weekend. And then I'll post that all on Blackboard so you can see everything as soon as I get it done. And then we'll talk about the exam on Monday. Okay? So look for raw scores soon. Raw scores on the multiple choice soon, and then look for full results maybe this weekend. Okay. Yeah.
What's the weighted ratio between multiple choice and
Forgot. I think it was 23 times 3, so 69 points multiple choice and 31 free response. Okay. What's that? Don't care. Don't count on it. Okay, so here we go. So I want to start by talking about this problem from the test, which was this one about a remote control car moving forwards and backwards. This was the rate of change function. And then I asked the question here, which one of these choices below shows the approximate rate of change function for the first 2 seconds using delta x equals 0.5. Where am I? So using delta x equals 0.5 and the left approach. And we want to, for the first 2 seconds. Okay, so we're looking for an approximate rate of change function. Okay, these are not functions. Okay, we'll talk about this later. So it's got to be one of these 4, and if we're using the left approach, that means we're pulling rates from the left side of the interval to be the rate for that whole interval. So now we're looking at B and E. These are used. This is the right side approach, using the right side of each interval. So then if we want from 0 to 2 seconds, this goes actually to 2.5. So it's E. Okay, so that E is showing for 2 seconds, it's showing an approximate rate function based on the left side of each interval. Okay, so, and then in number 5, it said estimate that number of feet moved in the first 2 seconds. So I think this rate function was called F. Okay, so to estimate that number of feet, we're going to add up all the total amounts of feet from these constant rates, right? So what's this constant rate at? It's f of 0, which is 0, okay, times delta x. And then, so that's going to be the little amount of change in distance for that first interval, and then we're going to add the next little amount of change, k delta x, so f of. So which rate do we use here? We use the rate at the left side, 0.5. Again, times the amount of time that went by, and then plus, etc. So each one of these is a little bit of change calculated by the rate times the amount of time. Rate times time is distance, right? So get one more there. I blew that. That's 0. And then the last one will be f of 1.5 times 0.5. Okay, and so this is what we use summation notation, right? So if we said like j, go from 1 to 4, and we basically have 4 different rates, so we'll call it k sub j for each of the rates times 0.5, k delta x, right? K delta x plus K delta x. Each K delta x, calculating a little bit of change for that 0.5 seconds. Okay, so this was the approach that we took to these sums as far as calculating an amount of change, right? This is like an estimated amount of change given a rate function. So this was like a rate of change and quantity approach to this topic. Okay, and we said if we wanted the exact distance traveled, what if we wanted the exact distance traveled in the first 2 seconds? So the exact number of feet the car has moved in the first 2 seconds. So that would be if we had infinitely small intervals and we added all infinitely many of those up this way, right? So if now instead of our intervals being 0.5, they were super, super small, and we had a zillion of them, right? How do we represent that? Integral, right? So that's what we learned. Integral is the total amount of change of a quantity whose rate is, in this case, f, as x changes, in this case, from 0 to 2. So it would be exact would be the integral from 0 to 2 of all of these, right? So it's, again, just k delta x. But now it's just the continuous function of those rates, and then the delta x is a really small change. Okay, so again, this is like the rate of change and a quantity approach to this topic. But if we look here, if you look, this 0.5 is what? It's this distance right here, right? That's 0.5. Or let's do this third one here, over here. So from there to there is 0.5. And then how is the f of 1.0 represented on the graph? Well, it's this height right here. That height right there is f of 1.0. Right? Y-coordinate, distance up from the x-axis. So we notice that we're multiplying this horizontal distance by this vertical distance. And so because our functions, we graph our functions in rectangular coordinates, that has a geometric meaning, right? Base times height is what? Base times height is area of a rectangle, right? So it's possible, and this is only possible because we graph in rectangular coordinates. So it's kind of, it's not the real meaning, it's like a coincidence. It's a coincidence because our x is this way and our y is this way, and that's how rectangles are formed. It turns out that these could also be thought of as finding the areas of rectangles. Like that right there. So base times height, 0.5 being the base, f of 1.0 being that height. Okay? And so that leads us to this right here. Okay? So that right there, if you think of these as base times height plus base times height plus base times height plus base times height, and you think of summing up for rectangles, well, that answer A then is representative in a geometric sense of the sum. So where all this other stuff we've done so far has been based on rate of change and quantities, so this would be like a geometric approach, and maybe what you're more familiar with from Calc 1. Okay? But it's kind of superficial. It's just a coincidence because of the way that our... This is much more meaningful. The way that we emphasized at the beginning of the course, talking about rate of change and quantity, this is just kind of, it just happens to work out that way because of the way we set up graphs. But the whole calculus world has kind of latched on to this as the real meaning. Okay, we kind of latched on to area as the real meaning with integral when the real meaning is about rate of change in quantities. Okay, about two quantities changing together, finding the total amount of change given a rate of change graph. Okay, given a rate of change, finding the total amount of change. That's our real profound meaning. And then this just happens to also work. Okay? This geometric approach. Okay, so then what would happen? What would happen if we took more intervals or made thinner rectangles? So actually, let's talk about this estimate. So this estimate of the total distance traveled, was it an overestimate or an underestimate? Yeah, because three of those rates are below. Only this last one is above. So that's an underestimate. So then sum of these areas then is an underestimate of what? Underestimate of what? Yeah, so let's think about, so if we made smaller rectangles, let's do it. Here we go. Ready? So here's something similar to what we have. If you're looking here. So if we made more smaller rectangles, and we look at what happens when you keep using more and more smaller rectangles. Oh, I meant 50, not 350. So here's 50. So what do you notice about now the sum of all those rectangles relative to the curve? It's kind of approaching. So now you see, so what's happening is that these more and more thinner rectangles do a better job, just like smaller intervals did a better job at calculating our total amount of change. More and more thinner rectangles do a better job of getting the area between the curve and the x-axis. Okay, so we're talking about then using integral. So integral would then be the exact area between the curve and the x-axis, and we think about it as like a zillion really skinny rectangles filling in that area and finding that area for us. Okay, so let's look at an example of using integrals as area. I gotta have my spiral notebook to take it. Okay, it's my spiral notebook. Here we go. So we're talking about integral as area. So let's say not as important as rates and quantities, but still important. No, there is usefulness. Okay, so there are geometry type situations that we use this for. Okay, so it does have application for sure. Okay, so an example would be find the area bounded by y equals 5x minus x squared and the x-axis. Okay, so let me just give you a warning here. One very common reason students blow these problems is because they don't read and get the right region. So they don't read carefully, they just they kind of graph the functions, and then they look at their graph, and then they kind of guess what region it's talking about without reading this really carefully. So when it's giving you the written description of the region, you have to make sure you have the right region. Okay, so my experience is that students blow that all the time. Okay, so this is an easy one, but I just wanted to warn you. This one's hard to get wrong, but other ones are easier. So if we graph 5x minus x squared, so one thing we could do is we could say, well, that's a parabola opening downward because it's minus x squared. And we could factor out an x to see that it has roots at 0 and 5. So somewhere it's going to have a high point, and then all right, so this is our y equals 5x minus x squared. And this is the x-axis. The x-axis is the horizontal axis. Okay, now here's another thing. If it doesn't say bounded by, or it doesn't say x-axis or y-axis in the description, then the x-axis or the y-axis are not part of the boundaries. So it's an easy trap to fall into. You've got 2 or 3 functions you've drawn, and you pick a region that has the y-axis as one of its sides, but they never said the y-axis. And if it never said the y-axis, or it never said x equals 0, then that's not one of the sides. Okay? Read the descriptions carefully. Make sure you have the right region before you dive into it. Okay, so we got this region here. It's going to be this right here. So what we want to do is we want to draw a typical rectangle or a typical strip. Okay, it's also my experience that students just blow this off. They just don't want to do this. They think, oh, he can do that if he wants. I don't need to do that. Well, when we get into harder problems, this is going to be allow you to do it. Okay, but if you never practice it, you get to a harder problem, then you probably mess it up because you didn't do this. So here's like a typical rectangle, or a typical strip. We're going to call it strip, all right? And the idea is that we're going to add up all the typical, that's a typical strip. We're going to add up all those typical strips, starting at x equals what? 0, and ending at x equals 5, okay? So we're going to add up all the typical strips from 0 to 5. So we need to find the area of a typical strip. So this is setup work now. So the area, S for, let's see, area of a, call it area of a rectangle. Okay, so we just need to find what the base and the height is. So our base is a little width right there, delta x. So we'll go with delta x. So when you do the typical strip, think about it as a finite actual rectangle instead of like a stick. So we'll do dx, delta x, and then what's the height of a typical strip? Okay, so it's the y coordinate of this graph. Do you see that that's just the y coordinate of this graph? So we could say y times delta x. It's just whatever if we're starting at the x-axis and we're going up to the curve, that's the y coordinate. But if we're delta x, then we need to write that in terms of x. So what is y in terms of x? What is the y coordinate on this curve in terms of x? 5x minus x squared. Okay, and so there is our area of our typical strip, R for rectangle. And so what are we going to do? We're going to add up all those, starting at x equals. So then we get the total area is total area of the region, call this R, is, how do we sum them all up as they get super, super thin? That's our integral. So our integral from 0 to 5, and this is still means sum. We're summing up all of these typical strips. So we write down typical strip, 5x minus x squared. Summing up the area of a typical strip. This is height, and this is base. So the dx absolutely has mathematical significance in the situation. It's not just something that you throw at the end of every integral, signifying you're doing an integral. No, it's mathematically the width of your strip. So it's part of the area. It's part of this typical area, and then you're going to S for sum up all the areas. Okay, and so then we can do that, and that's super easy. And whatever number we get for that, we do that. We do that integral. We get a number. What is that number? That number is the area of a region R. Found by, again, integral S for sum, summing up an infinite number of really thin rectangles, super thin rectangles. Okay, so for this, questions on that? I highly, so lots of you are looking at this and saying, oh, I could have just written that down at the beginning of the problem, okay? I highly recommend every single problem you go through this, because when things get more complicated, we start doing volumes, and then we start doing physics applications. This kind of thing is going to be very, very valuable. If it didn't feel valuable in this problem, it will be. So just get in the habit of doing it, practicing it. Okay, so what would, new question. What would, if I integrated from 0 to 8, represent? What would the integral from 0 to 8, 5x squared, 5x minus x squared dx represent in a geometric sense? Okay, you'd have more rectangles because you could be going all the way to 8 instead. Okay, so wouldn't we have to, why? Minus, what do you mean? Okay, so let's think about this. Let's graph this. Let's get a better picture. I'm about to erase. Any questions of all this? Okay, so let's take a look here. So what was it? Y equals 5x minus x squared? Okay, there we go. So here it is. And now we're going to integrate from 0 to 8. So let's go back to thinking about this as a quantity. What is 5x minus x squared if we're thinking about quantities? What is 5x minus x squared? What is that? What is that? Rate of change. So this is our rate of change function, right? So what's happening to our quantity from 0 to say 2.5? What about from 2.5 to 5? What's happening to our quantity? Still increasing, right? Because the rate's positive. But then at 5, what happens from 5 to 8? The total amount of our quantity will start going down because the rate is negative. So that takes that into account. It takes into account the fact that wherever the rate is positive, you're going to add to the quantity, and wherever the rate is negative, you're going to subtract. So we just need to think about that in terms of area. So in terms of area, what's it going to do? It's going to add up all these areas, but then what's it going to start doing from 5 to 8? It's going to subtract anywhere that the curve is below. It's going to automatically subtract out that area. Okay, so if we thought of okay, so if this was, say, R1 or A1, A for area, all this over here is A1, and then this, call A2, what does that, in terms of area, so what does that thing calculate? A1, so area is positive, right? So the A2, this is the positive area right there. And A1, this is the positive area right there. So this integral would calculate A1 minus A2. So it calculates a difference of areas. Whenever that function is below, it's gonna multiply what dx times a negative value. So all that's gonna contribute negatively to our total integral. So what was the first one we had was from 0 to 5, and that was what, 5x minus x squared? Okay, so if we had done that first integral, we would have gotten 20.8. Okay, so from 0 to 5, A1 was 20.8, or 20.83. So what are we expecting? What do you expect when I change this from 0 to 8? What are you expecting for the value? It would be definitely less than 20.8. Do you think it's going to be less than 0? Does it look like A2 is bigger than A1? If A2 is bigger than A1, then this integral should be less than 0. It is. So this then is equal to a negative 10 2/3. And you could do the math easily to verify that. So what if we actually wanted to calculate the total area? So if suppose we wanted A1 plus A2. How can you write an expression with integral, using integral? Okay, absolute value of the whole thing. If I do the absolute value of the whole thing, I'll just get positive 10 2/3, right? Okay, so one way to do that would be do the absolute value of your rate function, of your integrand. How can we do it without using absolute value? Right, you'd have to split it up. You'd have to take the integral from 0 to 5, and then do what? So you're going to do the integral from 5 to 8. We know that's going to be the opposite of A2. So to get it to add on A2, we're going to subtract, or take plus the opposite of that integral. So that would be how, in order to use an integral expression to get that total area, you'd have to add the A1, the integral from 0 to 5, minus or plus the opposite of the integral from 5 to 8 to make that thing positive. Okay, questions on that principle? So in terms of geometry, an integral, So people say, oh, it's area under the curve. Well, technically, no, it's difference of areas. So computing an integral in the most general sense, it's always correct to say that computes the difference of areas, not necessarily an area. It only computes an area if what? What has to be true for it to truly compute an area?
If both ends of the integral are above the x-axis or under.
And also what? Not only both ends, but everything in between.
Yeah.
So the whole, in order for this to truly calculate an area, f of x has to be positive for the whole interval. If it ever dips negative and anywhere between a and b, then that thing's computing a difference of areas. Any place where it goes below that thing gets that area gets subtracted from the total amount. Yeah.
But that's only true if we're trying to find it with respect to the x-axis, right?
Yeah. So with x up above is positive and y. So with the y-axis, it'd be left and right. So as long as it stays to the right of the y-axis, then it'd be an area. If it ever goes to the left of the y-axis, you'd be a difference of areas. Yeah. Okay. Other questions?
One more time, like the plus minus. Sorry.
What do you mean?
You said like you can't do absolute value.
No, you can do absolute value. You could.
Just that A2 part.
So if we wanted to actually get the total of these two areas, we'd have to split it up because the integral from 0 to 5 will be a positive, but the integral from 5 to 8 will be the opposite of this area, right? Because it'd be negative. So if I add the integral from 0 to 5 plus the opposite of the integral from 5 to 8, then I do get the total area a1 plus a2. Is it better? And you can also achieve that by doing that. So making that thing positive everywhere with it to have the same effect as doing this. Okay, another example. Where's my notebook? No, not this one. There it is. Okay. I still right on this page. So let's do another example here. I'm gonna make bigger notes for myself. Y equals 1/2 x cubed. One half x cubed, x plus y equals 6. And the y-axis. Why don't you practice seeing if you can get the right region? Okay? Can you get the right region? Y equals 1/2 x cubed, x plus y equals 6, and the y, so I should say r is bounded or enclosed by, bounded by.
What is that symbol? Sorry.
This
No, over one. Next to the R.
is,
Oh, okay.
right. So r is bounded by 1/2 x cubed, y equals 1/2 x cubed, x plus y equals 6, and the y-axis. Sketch the region. So hopefully you can sketch these without a graphing calculator, but there will be some where you will need a graphing calculator. But something as simple as this you should be able to do in Calc 2. Okay, so there are different possibilities of what you can interpret as the region here, just looking at the graph. But there's only one region according to the description. So can you identify where that is? So we want it's bounded by the pink one and the red one and the y-axis. So you should see that that's this right here. Okay. Okay, so we're going to start with typical strip. So we want to find the area. Okay, so a typical strip is just going to be, say, somewhere in the middle here. And the top is going to be the red curve, and the bottom of it going to be the pink curve. Okay, so what's going to happen is next week we're going to get to volumes, and we're going to take these typical strips and we're going to rotate them and come up with typical little volumes. So practicing this typical strips thing is important. Okay, so we want the area of the strip, and it's going to be, say, base times height. So let's do one thing at a time here. So what is the base? What is the base, or like the width of the strip? There it said delta x, right? So it's a little change in x. Okay, and then what's the height of this strip? So how do we calculate the height from here to here? Yeah. So let's start by saying that it's, what is it? It's the y coordinate. This height right here is the y coordinate of the red graph. So we'll call that y2. And this down here, it doesn't go all the way down to the x-axis. It goes down to the pink curve. So how far down does it go? To the y coordinate of the pink one. And so then to get that height of that thing, it's going to be the y coordinate of the red graph, or the line, minus the y coordinate of the cubic, the purple one. But since we're doing delta x, we need to express that in terms of x. So what is y2 expressed in x? That's the line, right? So it's going to be 6 minus x. So 6 minus x, y2, minus y1. And how is y1 expressed in terms of x? 1/2 x cubed. So that right there represents the height of the strip times the width, delta x. So we got it. So that's that's the height of the typical strip. And then what are we going to do? We're going to get the total area. We're going to sum up all the typical strips. So where's the first one? The leftmost typical strip, is that x equals 0? And then where's the rightmost typical strip? Well, it's whatever this is. So it's looking like 2, but we have to verify. The last little strip is going to be like right here. Got to verify where that is. So we've got to find the x coordinates such that the y's are equal, right? So we need the x coordinates such that those y's are equal. So we can do 1/2 x cubed equals 6 minus x. And so since we suspect that it's 2, let's just try 2. Does 2 work?
Yes.
1/2 times 8. Does it equal 6 minus 2? Yes. Because we're not really into solving cubics. Maybe you are. Okay. But so since we suspected it was 2, there's nothing wrong. We'll just do a quick check of it, and boom, it works. So that value is x equals 2. So we're going to integrate from 0 to 2. And this integral is s for sum, summing up all the strips. And so each strip has an area of 6 minus x minus 1/2 x cubed. That's the height of each strip times a little teeny width. And we're going to add a gazillion of those together, right? So this ability to see that this thing is y2 minus y1, y2 being the y coordinate of the red line and y1 being the y coordinate of the curve is going to be really important when we get into these really crazy solids of revolution. Okay, because we're definitely going to need that. Okay, so that's another easy one. Do the math. And we know that the answer then will be the area of that region. Please.
What was the purpose of doing 1/2 times 8 equals 6 minus? Why did you solve for that?
Say it again.
Why did you solve 1/2 x cubed equals 2 minus?
We needed this. We needed what? So we were looking at the bounds. Like the first. So the first strip is at x equals 0, and then we got all these strips from 0 to where's the last one? We're trying to find what x value that was. So I was trying to find this upper bound of integration. Yeah. Other questions? Okay. So what if? So same. New example. Maybe I should erase. So, last chance for questions on this one.
How did you find it?
Okay, so how I need to get this distance, right, from here to here.
Oh, okay.
Do you see it?
Yes.
So it's the y coordinate of that, the straight line, minus the coordinate of that there will give you that height of that rectangle.
Right.
Yeah. Okay, last chance. Last chance for questions. Okay, so same curves. So new example. So what about the x-axis? So find the area of R, which is the region bounded by x plus y equals 6, y equals 1/2 x cubed, and the x-axis. All right, so first of all, do we recognize what region we're talking about? So it's going to be the region that's formed by our two functions and the x-axis. So we should easily see that that's this down here. Okay, so we're going to start with, so this is our region. Shake that without. Okay, so we're going to start with typical. So, this is our. So typical strip. Top of it is okay, so we got this, and our area of our strip is going to be, what's the top, or what's the height of it? Y coordinate. And that y coordinate is it 6 minus x? So, what do you think of that? So I do the same thing I did before. I draw my typical strip. The height is going to be the y coordinate of this red graph, 6 minus x, times the base, or times the width of it, delta x. So some of you are feeling uncomfortable, and that's good. Yeah.
Like, wouldn't the first half of it actually be the first function?
Yeah. Look. So this, if you notice, this region goes all the way from x equals what? 0 to 6. Okay. And when we start at 0, so over on this left side of the region, is this the area of a typical strip? No, so you've got a different typical strips defined differently than the one I drew. So over there, your height is what? What's your height of that strip? It's a different y coordinate. Yeah, so for this one, it's going to be, the height is going to be 1/2 x cubed, and then times the width is delta x. So as we go from 0 to 6, it's like the boundaries change. So there is no one typical strip. There is no one typical strip from 0 to 6. It changes. There's actually 2. Okay, but many of you are thinking, so if we want to find the total area, then what do we need to do? Yeah, you're just going to have to add 2. You're going to have an integral where this function is governing how tall the strips are, and then it's going to change. And the other function is going to, for the rest of the way, from left to right, this other function is going to govern how tall the strips are. So you're going to have to add 2 integrals together. And so, can you finish this problem while I take attendance? Okay, finish this problem. Work together. Okay, so you should have gotten. So I defined both typical strips. So it's going to be 0 to. So we need. Oh, we got that. It was already. So 0 to 2 of 1/2 x cubed dx plus 2 to 6, 6 minus x dx. And did you guys get an answer? Total answer? I'm hearing 10. That's pretty cool that that weird looking shape has an area of exactly 10, right? Okay, so is there a way to do it with just one integral? So is there possible that we could do it with just one integral? Okay, so what we need, everything we've done so far has been these vertical strips, right? So what if could we do a horizontal strip? So if we do a horizontal strip, then does that represent a typical strip for the whole region from, now we're doing it from bottom to top? So the first one would be down here, and then we'd have all of them stacked up like this, and the last one would be here. Do they all have, are they every single strip defined the same way this one is? Right, they are. Okay, so we're going to do it this way. So we're going to do the area of this strip is going to be, so base times height. So what is the base of, let's just do the width, right? So what is this dimension of this thing here? How would you calculate that dimension? But it's not a delta x. We think of a delta x as kind of smallish, right? So it's this distance right here is that long dimension of that rectangle. And how would we define that? Those are both x coordinates. It's the x coordinate of the red graph, call it x2, and the x coordinate of the cubic, call it x1. So therefore that distance from x1 to x2 is what? No, just in terms of x and x's, just in terms of those. He wants x2 minus x1. What do you think? Yeah. Again, when we get into these volumes of revolution, this is going to be an important skill that you can just recognize x and y coordinates on a graph. It's going to get complicated and confusing, and my experience is that students have trouble just recognizing that this right here is an x coordinate. It's the x coordinate of this point. So from here to here is the x coordinate of that point right there, and then from here to here is the x coordinate of that point. So then that distance is going to be the final x minus the initial x, or x2 minus x1. And then what is our tiny width? Delta y. So this slice is x2 minus x1 delta y, but since if we know it's going to be in terms of y now, so we've got to write what is x2 in terms of y. That's our line, so we're going to solve for x. It'll be 6 minus y. So we had x plus y equals 6. Solving for x is 6 minus y, and that's our x coordinate of this red line. Okay, what is x1? Well, we had y equals, this curve right here was y equals 1/2 x cubed. So what is x1? We got to solve for x. 2y equals x cubed. X equals the cube root of 2y. So we got 6 minus y. That's x2. Minus x1 is the cube root of 2y delta y. And there we've got it. And so we can do this in one integral by doing the integral from what to what? So so now we're stacking vertically. We're doing it in terms of y, then we're looking at the lowest one, the lowest typical strip, up to the highest typical strip. And so we need that y coordinate, and we know that the x is 2, so we can plug it into either one, and that gives us a y of 4. So here y equals 4. So we're going to go from 0 to 4 and add up all those typical strips. 6 minus y minus 2y to the 1/3 dy. And so, again, you guys can do that, but let's verify it. So we're going to go from 0 to 4. What's that?
Why the intervals 0 to 4?
Okay, because our typical strips are horizontal now, right? So instead of lining putting them like books,
Okay, now I got it.
so we're now stacking those typical strips from the bottom of it horizontally up to the top. So our first strip is y equals 0.
Oh, I didn't realize that the intersection was at 4.
Yeah, because we know that the intersection was at x equals 2, and that would mean that y would be 4.
Okay, gotcha. Thank you.
So we got 6 minus y minus 2y to the 1/3 dy. Oh, you're kidding me. It's gone. With a push of a button. Try it again. 0 to 4. 6 minus y minus 2y to the 1/3. Okay, don't. 8y. Well, it's not saying it's exactly equal to 10. So the other one was exactly 10. So I'm assuming it's doing some kind of numerical technique to find that, and it's giving us a very close approximation. So, okay, questions on this one?
That's weird. I got 9.9.
Yeah, so yours is doing. Yeah, it's the same thing. Our calculators are doing a numerical process. It doesn't have this integral in its memory banks. Okay, it's doing a process like it's adding up a bunch of rectangles. Okay, so it's adding up a bunch of finite number of rectangles to get a really close approximation. And that's what your calculator is doing too. Okay. What's that? Well, it depends. It really depends on the situation, whether you want to use vertical or horizontal. Let's see, is that it? Oh, no, one more. Okay, so one more. Okay, so find the area enclosed by x equals 1 minus y squared and x equals 2y squared. So my experience is if students are not very good at sketching graphs where it's y equals a function of x, they're really bad at sketching x equals a function of y. So this is important that you're able to sketch, because if you solve for y and then put that in your calculator, you won't get exactly what those curves are. So you have to have some strategy for being able to sketch those, because if you switch it around and solve for x, you're not going to get the whole curve. So what's one strategy for thinking about how to graph x equals, say, 1 minus y squared or x equals 2y squared? So, yeah, so do you know what y equals 1 minus x squared looks like? Oh, that's sad. Really sad, guys. What is minus x squared? What is minus x squared and then add 1? Yeah, it's gonna be minus x squared and then move it up 1. So if that's 1 minus x squared, then what's x equals 1 minus y squared? Opening left or opening right? Opening left, and with its vertex at 1. 1, 0, right? So it's going to open left, and it's going to be shifted 1 to the right. So if you put that in your calculator and you solve for y and you get whatever you get, you'll only get the top half. If you don't do plus or minus when you take the square root, which most students forget, then you're only going to get the top half of that thing showing up on your calculator, and it won't be correct. So you got to have the whole thing. So these x as a function of y types of easy ones, you've got to have a system to know how to sketch those. Okay, what about x equals 2y squared? So use the same strategy. Think about what y equals 2x squared equals, and then we're going to just put that on, kind of swap the axes. So that's going to look like this. Notice what's missing here from it says find the area enclosed by these two curves. What's not involved? X-axis, y-axis, not involved. Therefore, the x-axis nor the y-axis should be boundaries of your region. Only these two curves. So do you see the region? Question?
So would the integral be from 0 to wherever the other point crosses the x-axis, and then the 1 minus y squared minus 2y squared?
Let me get a picture of it here. Better colors. All right, try me again.
So the integral of...
You're already writing the integral? I don't recommend that. I don't recommend going right for the integral. Let's figure out what our typical strip's going to be like and get the area of the typical strip. So that's what I would recommend. Because when we get harder problems, especially these volumes, you want to have that under your belt. So I would not go straight to trying to write an integral. Okay, so here it is. So we want to ask the question: do we want our typical strips to be in terms of x, meaning up and down, or in terms of y, left and right? Yeah, this is a lot better to do in terms of y. If you do it in terms of x, then look, you're going from one curve to the same curve. See that? So it can be done, but it's not convenient. And not only that, but then you have two different, you'd have to split it up. You'd have to go from blue to blue, and then over here from red to red. Instead, do a typical strip this way, and then can we get away with one typical strip for the whole region? Yeah. Yeah, so the first one would be here. Look, the first one would be at the bottom right there, and then we'd have them all like this. And then the last one would be all the way up there, and they all have the same left boundary and right boundary, so it's one typical strip does it. Okay, so area of the strip. First of all, delta y or delta x? Delta y. So what we got left is, how do we get that distance right there? So in the most general sense, it's what? An x coordinate out to the far right minus the x coordinate at the near right, right? So this is like x, kind of made a mess here, but it's going to be x2 minus x1. x2 is what? Here's another reason why this is much better with delta y, because what is x2? You're looking at it. There it is. It's the red curve. So it's just 1 minus y squared. x2 is 1 minus y squared. What is x1? 2y squared. So this particular problem is far, far, far easier and convenient to use delta y. So now that's our typical strips, and then we're going to add up So from what to what? That's the question. No, not 0, because we've got horizontal strips. So we're not going from left to right. We're going from bottom to top. We're stacking them up from bottom to top. So we need, this is our first strip. Is at what y value is this? How do we find it? Well, it's the y value where the x's are equal. So we do 1 minus y squared equals. Looks like 3y squared equals 1. So y equals plus or minus radical 1/3. So our first typical strip is going to be at y equals negative radical 1/3. And our last typical strip is going to be up here at positive radical 1/3. And we're going to add them all up. It's going to be 1 minus y squared minus 2y squared dy. So on your homework, I highly recommend practice this typical strip stuff. Don't just look at the region and try to write down the integral. That practice of doing that will be very helpful next week when we do these difficult volumes. Okay, that will be very helpful. Last chance for questions for this one.
Just like technique to draw x and
Say it again.
technique to draw x equals. You just go solve for y, plus or minus.
Yeah, you gotta have plus and minus. Remember that two integrals. Now you have to add up those plus those, right? Different boundaries.
Or like when I go to draw, I still solve for y, just love my
The only part I have trouble with is graphing it initially. So if I were to solve for y, I'll draw the one curve. I just remember that I have the other side, just
Multiply by 2 or something?
or just whatever that is, just do the same y. As long as it's
Yeah,
as long
just
as
don't
it's
forget.
y squared, yeah.
I mean, maybe.
But what's
But-
the technique though? I never learned that.
What's the technique?
Whenever you want to draw x equals
One possible strategy is so do you know what, can you sketch y equals 1 minus x squared? Right? What's that?
What's the
Well,
parabola starting at 1 max?
it's going to be up at
negative
1, it's going to open downward.
Yeah.
Well, now, so then if it's x equals 1 minus y squared, so this is opening on the negative y-axis, right?
Right.
And then its vertex is at positive 0, 1. Well, then this is going to open on the negative x-axis, and its vertex is going to be at 1, 0. It's just going to be flipping the axes, right? So it's going to open in the negative x direction from 1, 0.
Okay.
You see?
So you're just thinking in that way. Okay.
And this is going to open from the origin on the positive y-axis. So, sorry, y equals 2x squared is going to open on the positive y-axis. So x equals 2y squared is going to also start the origin and open on the positive x-axis. There it is.
Okay, that's easy.
Make sense?
Yeah, I don't need to do all that crazy
Yeah.
stuff.
I wish that was on video.
What's that?
I wish that was on video also.
What we just said did?
Yeah.
I'll leave it. It's still recording.
Oh, good.
Yeah.
Those videos are great.